Hey everyone, this is lesson 27, part 2. Now in part 2, we're going to combine some of the things we've learned already, like rational root theorem and remainder theorem and synthetic division, and we're going to use that to find either roots or factors of cubic polynomials. And there's two problems we're going to go through, and they may take a decent amount of time through each one, so I think I'm going to break this up into two videos, a video 1 and a video 2. Video 1 is going to address question type 67. So here we go with the first video. So question type 67 says identify the roots of f of x, and f of x is this cubic polynomial right here. F of x equals 3x cubed plus 12x squared minus 12x minus 48. So the process of finding the roots, now remember roots are the x-intercepts or the zeros. So these are the values of x that make the polynomial equal 0, which could be useful if you're using this polynomial to model something that's happening in the natural world. But anyway, jumping right into it. We want to find the roots of this polynomial, and that involves some trial and error. We've got to essentially take a guess as to what one of the roots is, test it, see if it's a root. If it's not, move on to the next one. And we're going to use rational root theorem to help us figure out where we should start. So we start with the simplest roots using rational root theorem. So we're going to use rational root theorem for this polynomial. And remember from part 1 of lesson 26, that involves listing the factors of q, which would be the constant term, over the factors of p, which is the leading coefficient. So the constant term is negative 48, so we know that's going to have a whole bunch of factors to it. So if you imagine listing out the factors of 48, right, we know 1 goes into 48, as does 2, and 3, and 4, not 5, but 6, and then 8, and 12 goes into 48, and 16 goes into 48, and 24 goes into 48, and then of course 48 goes into 48. Okay, so a decent number of factors for our constant term, and then our leading term is 3, so we have down in the denominator we have the factors of 3, which is plus or minus 1, and then plus or minus 3. Okay. So here's where we can decide how much of this makes sense to do. If the question was identify all the possible rational roots of this polynomial, then we would need to go through the process like we did for rational root theorem in the previous video, where we would divide each of these numerators by each of the denominators and get all the possible combinations. Fortunately, we don't have to do that. Okay, we're just trying to figure out what are some good numbers we should start with, right? We know if we were to list out all the possible combinations of these, all the numerators would go over plus or minus 1, right? Which means the numerators just become essentially what they are. So we could start looking at maybe just these few factors right here, or possible rational roots, right? We're going to test these, and then if none of these turn out to be roots, then we can come back up to the list and get some of these. So that's what we're going to use rational root theorem for this context, is just figuring out, okay, what values do we want to start testing? We're going to start with positive 1. That'll be our first one. So we're going down here and we're going to test x equals 1, or x equals positive 1. The way to test to see if that's a root of f of x is it should make f of x equals 0, right? So we're going to use remainder theorem. Now, when we learned remainder theorem, we learned it in terms of dividing by polynomials, by linear binomials. So in this case, when we're dealing with x equals 1, this is the first one that we're testing. Okay, that's associated with the linear binomial x minus 1, right? Because if you've got the factor x minus 1, okay, let's say that's a factor of your polynomial, then you associate that with a root or x-intercepts of x equals 1. Okay, and when we learned remainder theorem, we learned that, well, if we think of our binomial as x minus c, then we want to evaluate f of c. If we evaluate f of c, whatever the answer is the remainder. Okay, so in this case, c would be 1. So we're going to find f of c, or f of 1. So f of 1 is equal to 3 times 1 cubed plus 12 times 1 squared minus 12 times 1 minus 48. And we're trying to see, does this equal 0? Right? So 3 times 1 squared cubed would be 3, say plus 12, minus 12, minus 48. Oh, let's see, that equals 3 plus 12 is 15 minus 12, so that's 3 minus 40, that's going to equal negative 45, right, which does not equal 0. So because this doesn't equal 0, that means we don't get a remainder of 0, if you remember remainder theorem. So what we've determined is that x equals 1 is not one of the roots of that polynomial. That means x minus 1 is not one of the factors. Okay, let's test x equals negative 1. So we're going to evaluate f of negative 1, and that's going to equal 3 times negative 1 cubed. So we're just plugging in negative 1 for x, plus 12 times negative 1 squared, minus 12 times negative 1, minus 48. Okay, that will equal, let's see, 3 times negative 1 cubed. Negative 1 cubed is negative 1, so that's negative 3. This is going to be plus 12, and then this is going to be plus 12, and this is minus 48. So negative 3 plus 12 is 9, plus 12 is 21, minus 40 is, so this equals something like negative 27. Okay, definitely not 0. So unfortunately, that means that x equals negative 1 is not one of our roots, and therefore x plus 1, which would be the associated factor, x plus 1 is not a factor. So we can get rid of those, and now we start crossing our fingers and hoping that x equals 2 works for us. Okay, so to evaluate this, we're going to find f of 2. F of 2 equals 3 times 2 cubed plus 12 times 2 squared minus 12 times 2 minus 48. Okay, so that's 3 times 2 cubed. 2 cubed is 8 times 3 is 24. Plus 12 times 2 squared. 2 squared is 4 times 12 is 48. Minus 24 minus 48. Well, look at that. That's 24 plus 48 minus 24 minus 48. Well, that equals 0. Okay, that's good news because that means that x equals 2 is one of the roots of this polynomial, and we can imagine then that x minus 2 is one of the factors. Okay, so good. So we can work with this. Now, we could continue to use remainder theorem like we've done here and try to test all these other possible roots until we find the one that's the root of our polynomial, but there's a better way to continue on. What we're going to do is, now that we've identified one of the roots, which means we actually know what one of the factors is, we're going to imagine taking our original polynomial, our cubic, and if we divided it by that factor that we identified, so in this case we tested, we tested x equals 2, so the factor is x minus 2. If we imagine dividing x minus 2 out of this polynomial, what would be left would be a quadratic. So this polynomial is equal to x minus 2 times some quadratic. If we could figure out what that quadratic is, then we can use that to very easily get our remaining 2 roots, because the remaining 2 roots would have to be the roots of this polynomial, or this quadratic. When I say remaining 2 roots, I mean that this is a cubic polynomial, so when we're asked to find the roots, we should be able to find about 3 roots, unless there's one that's repeating. And since we've already found one, we only have 2 more left to find. So we're going to use synthetic division to do this. You could use long division, but what we're going to imagine is dividing our polynomial by x minus 2. Divided by x, the factor x minus 2, or using the root x equals 2. So for that, we're going to set up our synthetic division and put 2 in the box here. If you don't remember synthetic division, you can go try the video. Then along next to the box out here, we're going to include the coefficients of our polynomial. So that's going to be 3 and 12 and negative 12 and negative 48. Okay, then we start the process of doing the synthetic division. Right? So remember, synthetic division means you take the first term and you just drop it below the line. Then we say 3 times 2 is 6. 12 plus 6 is 18. 18 times 2 is 36. Negative 12 plus 36 is 24. 24 times 2 is 48. And negative 48 plus 48 is 0. Okay, good. We expected to get 0 as our remainder. Remember, that's the last term, the term at the end when you're doing synthetic division. We expect to get 0 as a remainder because we had tested and determined that x equals minus 2, or x equals 2 is a root, or x minus 2 is one of the factors. So we would expect to get 0 if we divided our polynomial by x minus 2, which is what we did. More importantly, we now have this. This is our quadratic. This is what we were looking for. We can see our quadratic now is 3x squared plus 18x plus 24. So this is the quadratic that remains if you divide that cubic, our original problem, by x minus 2. Now we can use this quadratic to find the remaining 2 roots. So if I bring it down here, 3x squared plus 18x plus 24. And since we're trying to find roots, which are values that make it equal to 0, I'm going to set it up as a quadratic equation, meaning it's equal to 0. And now we can use factoring or quadratic formula or whatever we think might work. You'll notice then that before we even start factoring, before we try to do any slide and divide or anything like that, there is a term we can divide out of all of these. There's a factor, rather, we can divide out of all of these terms. You notice that all these coefficients are divisible by 3. So we can turn this into 3 times x squared plus 6x plus 8. This is what you get with each term when you divide the 3 out. And now x squared plus 6x plus 8 becomes something that's easy to factor. We need 2 numbers that multiply to give 8 and add to give 6. Well, that would be positive 4 and positive 2. So now that we've factored this polynomial, now we know what our remaining 2 roots are. And remember, for roots, you just imagine setting each factor equal to 0. So here we have x equals negative 4 and x equals negative 2. Okay, and our original one we found is 2. So the answers are 2. So the 3 roots of f of x are, we know that x equals 2 is a root, we know that x equals negative 2 is a root, and we know that x equals 4 is a root. Those are the 3 roots with our cubic polynomial. So in the next video, we will try finding factors, which will involve the same process. And let me know if you have any questions. I'll talk to you soon.